Perfect. So the second speaker of today is going to be Matheus Ota, who is a PhD student in the Department of Combinatorics and Optimization at the University of Waterloo. His research interests include vehicle routing, combinatorial optimization, integer programming, and stochastic optimization. He holds both a master's degree in computer science and a bachelor degree in computer engineering from the University of Campinas in Brazil. Please go ahead.
Okay, just one sec. Just set the timer here. 1 sec. All right. Well, thanks the organizers for inviting me to give this talk. And I'll be talking about combining column generation with column elimination. This joint work with a lot of very good people. Andre, Ricardo, which is my supervisor, Anthony, and Willem. So the class of problems that we're trying to solve here are these vehicle routing problems with intra-route constraints. Here we are given a diagram of D where S and T corresponds to the depot and V plus is my notation for the set of customers. Small c here are the R costs. Our goal is to cover V plus with some ST paths P1 all the way up to PK, such that we minimize the cost of the paths being used. By cover here, I mean to visit exactly once each of these customers, and C of PI is just a shorthand for the cost of the arcs inside path PI. And what I mean by intra-route constraints here, these are constraints that affect the feasibility of a single path, but not of a collection of paths. So we model this with this black box feasibility function f of p that returns a binary number, indicating if the path is feasible or not. Okay, let me denote then by PF the set of feasible paths. We have then this set partitioning formulation here, where I have a binary variable lambda p, indicating if we use path p or not. And this is just how many times vertex v appears in path p. So this is just saying that we need to visit exactly once each of these customers, and this is saying that we select exactly k paths. So as many of you know, we have too many variables here. So one would typically solve this formulation with column generation. In particular for vehicle routing problems, people usually model this pricing problem as a resource constraint shortest path problem. And this works well in many cases, but depending on the choice of your feasibility function f, such an approach may lead to an explosion in the number of labels or states explored by the RCSPP solver. And I'll detail a bit better this last point now. So to explain a bit better, I need to explain better what are elementary paths. So say the ST path like this is elementary if all these customers are distinct. And this is my notation for the set of all elementary ST paths. It is known that pricing over elementary paths is strongly NP-hard, so what researchers do is that they replace this set with some relaxed set of paths, either this or this one. In particular, this NG path relaxation is known to produce a very good bounce for many vehicle routing problems, and it's what we use here. So to understand better this point, we consider a first example of the problem in the previous slide, which is perhaps the most basic example that one can think about, which is this capacitated vehicle routing problem. Here, a path is said to be feasible if and only if the demands collected by the path is at most the vehicle capacity. And to get a stronger bound, rather than just having PF here, I have the set of paths that satisfy this capacity, and they are also elementary. The problem then is that because of this result, pricing over this set is too hard for me to do. So what researchers do is that they replace this with this relaxation NG. And it's fine to relax the set of elementary ST paths because these constraints guarantee that I will only select paths that visit each customer exactly once. Paths that visit each customer at most once. Okay, but a motivating example then for this work is this chance-constrained VRP with stochastic demands, where now the demands are random and represented by this random vector D. And then I will say that a path is feasible if and only if, with high probability, the demands collected by the path fits into the vehicle. So this is epsilon here is just a small parameter. And it was shown by Taidin, Ricardo, and Jim Lutke in 2018 that if the probability distribution P is given by scenarios, then even pricing these non-elementary paths in PF is strongly NP-hard. What this means is that if we use the previous trick that I had shown on the previous slide, this will not work here, because even if I didn't have this blue set, just solving the pricing problem over PF is already too hard for me to do. So in fact, the formulation that they're using that work is what motivates our work here. Okay, so what is the baseline formulation that we use? Let Q be a relaxation of the set PF, such that pricing over this set here is easy, meaning that I can solve this quickly with existing RCSPP solvers. And then I have this other formulation here, x of f, that essentially is just blocking me from using any path that it's infeasible. So this is just saying that you cannot use all of the arcs inside an infeasible path. And the idea is that this allows me to use some infeasible paths, but these are blocked in this part here. I should say that if you have other formulations that do the same thing about blocking you from using feasible paths, then you can use this in place of these simple constraints here. Now, once you have these two ingredients, what you do is we replace this set with this blue set. And then all the way up to here, we have the same formulation essentially. Then we have these linking constraints that are mapping from the lambda variable to the x variables. And then I'm blocking from using infeasible paths. And I'll call this the master formulation, and I'll denote it like this. And this is to highlight that I really care about the set of paths where the lambdas are being defined over. Okay, and it is easy to see then that the inequalities defining this set are robust, not in the sense of robust optimization, but in the sense of branch cut and price algorithms, because you don't have lambdas here. And then you can just give this master formulation to branch cut and price generic framework, such as VRP solver, and solve it like this. And essentially, this master formulation is the approach that was taken on the previous work that I mentioned. Okay, so what is the main idea of our work? So on one hand, we have this master formulation defined over this set, which is a relaxation of this set here. But what I really want is to have the bound with this formulation here, but the problem is that pricing over this set is too hard for me to do. So the idea then is to apply column elimination to get somewhere in between. So I get some Q prime that is in between the red and the blue one. And maybe this allows me to get better bounds without making pricing too hard. Okay, having said this, let me denote our set of resources such that the resource constraint ST paths in D corresponding to R gives me the initial relaxation Q. And let A be an RCSPP solver. For example, you can think of A as these labeling algorithms that people usually use for solving the pricing problem. And we assume that A here gives me already paths that satisfies the NG path relaxation constraints. So the path belongs to P and G. So here's the main algorithm. We initialize Q prime and D prime like this. Then we solve the LP relaxation of that master formulation using algorithm A to solve the pricing problem. Then we get some lambda bar. Then I look at the support of lambda bar. If there is a path that it's infeasible in this support, then I refine D prime to eliminate that path, and I update the relaxation Q prime accordingly. This is different than just doing column generation, because column generation is just solving this master formulation once. But this is also different than column elimination, at least as it was proposed in the paper by Anthony and Willem, because we're not solving network flow models over these state transition graphs. And I'll explain this better on the next slide and what I mean by refining here. Okay, so as I said, column elimination is based on these state transition graphs, where nodes correspond to states and paths correspond to solutions. So here's a picture to illustrate this. Here's the original input graph D, and here's a diagram associated with this input graph D. Each of these nodes correspond to a state. For example, here the first entry denotes the customer, and the second entry corresponds to the consumption of some resource. The relaxation here are all the paths such that the total resource consumed is at most 3. And observation nice to have here is that if you're using algorithm A to solve the pricing problem, then essentially what this algorithm is doing is finding a shortest ST path in a diagram like this. But because of the way these algorithms are implemented with many dominance rules and smart implementation tricks, they don't really explicit construct this diagram, which is different than if you solve this with network flow, where you really create all of these states. Okay, having said this, let me explain what is column elimination. So suppose the path P prime like this, 1, 2, 3 is infeasible. So this function returns 0. So P prime is being represented here in this diagram. What we do in column elimination is that we create a new node with more information in this node so that we eliminate that path. So here I'm creating this node where I'm now a customer 2 with resource consumption 2. And I remember visiting 1 before. I delete this arc and I redirect it to here. Now from here, I cannot go to 1 because I already visited 1 before. I cannot go to 2 because I'm currently a customer 2. Also, I cannot go to 3 because this was assumed to be infeasible. Okay, so you repeat this, and this is what column elimination does. It keeps eliminating these infeasible paths. And the simple observation that we had then is that you can essentially apply the same reasoning to the input graph T instead. And here's an illustration to show this. Again, suppose that this path is infeasible. Here's your original graph. What I did here is that I created 2 new nodes with more information in these nodes. Here, this is representing the set of vertices that I exactly remember visiting before. So here I am a customer 1, and I exactly remember visiting the depot before. Here I am a customer 2, and I exactly remember visiting the depot and customer 1 before, and so on. And here, because there are many different ways that you can reach this node, I don't have any memory here. All right, and you can check then that you don't have a path here that maps to this P prime. A consequence of this then is that if you run your pricing algorithm A over D prime, you're effectively optimizing over this set because A was assumed to find paths that belong to P and G. You find paths that belong to Q because this is how I define the set of resources R. And you don't find P prime because P prime is not a path in this graph anymore. Therefore, this is exactly how you perform the refinement operation that I have shown on the algorithm earlier. So we conducted computational experiments with this Babcock or VRP solver framework. And I should say that this is a generic framework that gives you a lot of these features that people have developed over the years, that you get all of this for free if you use this. So we solved the root using CG+CE, and we run the loop for at most 20 iterations. And in each iteration, we eliminate at most 50 paths. I'm omitting here the results using CG+CE and this state transition graph. So it's bad to refine this state transition graph, at least for this method. It's better to refine the input graph instead. Okay, and we use the same instances and cuts from that previous work, which is the state of the art. This is the relaxation that they use. Essentially, they have one single resource for the expected demand values, and they show you how to set this capacity value. The time limit was set to 1 hour. CG is just VRP solver plus these cuts. CG+CE is our proposed approach, and CE is the recently proposed column elimination method. And here's a table with our results. LPG represents the LP gap at the root node. TS is the total runtime, and this is the number of eliminated columns. You can see that mostly we achieve better root gaps and better runtimes than the other methods. In particular, we solve many of these instances at the root. And also, well, this is the previous state of the art. So we close 3 open instances with respect to the state of the art. But also note here that column generation could already solve 2 of these open instances. And this could be probably because this uses VRP solver, which has many features that was not implemented here. But we can also solve 1 open instance with respect to column generation. Also note that we achieve generally better root gaps than just column elimination, and we eliminated a smaller number of columns. And this might be because we're leveraging this pricing algorithm that VRP software has to find the paths, while maybe column elimination is refining diagrams, refining paths that would never be founded by our approach. Okay, and I should also comment that we also conducted experiments on this one commodity pickup and delivery VRP problem, where the state of the art is this previous work here. Our approach could also improve upon the state of the art, but what happened here is that I also managed to derive some new cuts for this problem, and these new cuts makes just a column generation based approach already very efficient. So although this improves the root gap, I will not claim that this is better than column generation for this problem. And a more general conclusion here, I think, it's, in my opinion, the main tool of this column elimination method is that combinatorial refinement operation. And while previous works applied this tool to refine these state transition graphs or decision diagrams, for example, what we did is that we apply that tool to refine the input graph instead. And this gave us a fairly simple but generic tool that allows us to easily incorporate column elimination into some state-of-the-art BCP algorithms. For the future, we plan to apply this to some other problems, but perhaps a more open-ended question is, in what other settings of integer programming can one leverage this combinatorial refinement operation? So thank you very much for your time, and that's all.
And thank you for the very interesting talk. And now we're gonna move to the third one,